So hi everyone, my name is Richard Combe. I'm going to present to you this paper called Unimodal Bandits with Continuous Arms, Order-optimal regret without smoothness. So this is a joint work with my colleagues Alexandre Protière and Alexandre Fouquet from KTH. So without further ado, what is a bandit problem? So a bandit problem, the simplest of all bandit problems is called a classical multi-arm bandit, which is a model for the following situation. So let us assume that you have a finite number of patients whom display the same symptoms, and you have two treatments that may or may not be effective, and you want to find out which one is the best. So of course, the goal here is that you would like to maximize the number of patients whom have been allocated the good treatment, assuming that one is more effective than the other statistically. So the question is now, without any prior information when you begin the experiment, how should you choose? How do you choose based on successes and failures? And the main feature of all bandit problems is that there is always a trade-off between exploration and exploitation, meaning that there is one good choice, one bad choice. However, in order to eliminate the bad choice, you have to try it at least a few times. And the amount of the performance measure for these kind of problems is what we call regret, which is more or less proportional to the amount of times that you have to try out bad decisions. Okay, so we call this a trade-off between exploration and exploitation. So now here we are considering the continuous bandit problem. So what is the continuous bandit problem? So we assume that we have an unknown function from a bounded interval into to 0, 1. So this function is the reward function. It is what we would like to maximize. And we would like to find x star, which is the place at which this function is maximal. So of course, since we do not know mu, the problem goes as follows. So first, we are given no prior information. And at each time, so we have t trials in total, we can select one point between 0 and 1, and we observe a random variable, a random reward, called xn of xn. So what is xn of x? It is simply an IID sequence whose expectation is equal to mu of x. So in other words, at each trial, we are allowed to select one point within the interval 0, 1, and we observe a noisy realization of mu of x, which is the function value evaluated at that point. All right, so it's simply a generalization of the classical bandit problem to a continuous setting. So there are two performance metrics that we would like to consider. The first one is called regret. So the regret, R of t, is the difference between what you would get if you always chose the optimal value, so t times mu star, and of course minus the cumulative reward that your strategy yields. So it's the sum over n of the expected value of mu of xn. It is the difference between the rewards obtained by an oracle that knows mu and you, who has no prior information. All right. And another performance measure, which is classical for people who do optimization, is simply the optimization error. It is the difference between mu star, the optimal value of the function, and mu of xt, which is the last point selected by the algorithm. So it is noted that to get a small regret, we need to have a small optimization error, but the contrary is not true. There are some algorithms that have a small exploration, a small optimization error, E of t, but a large regret. Okay. So now, what are the assumptions that we are working with? What are we allowed to exploit? So we are going to assume that mu, the reward function, is a unimodal function, meaning that it is first increasing before x star and then it is decreasing, unimodal. And the function is similar to c, a constant, times x minus x star to the alpha, where c and alpha are both fixed, but they are unknown. Okay, so we do not know the c and the alpha, and in particular, the parameter alpha, we call this the smoothness of the function. For instance, if alpha equals 2, the function is quadratic near its optimum. If alpha equals 1, it is more or less similar to the absolute value, and so on and so forth. So hence the name Unimodal Bandits, unimodal functions, without smoothness or without the knowledge of the smoothness. So first of all, it should be understood that the optimal regret that can be obtained is up to a logarithmic term proportional to square root of t. So it is typically something like square root of t times log of t. So you may be wondering, what are the known approaches in order to get order-optimal regret? So the first approach is a discretization approach. So discretize the problem finely enough, and then apply a problem for the classical bandit, for instance, the UCB algorithm, upper confidence bound algorithm, which is a classic algorithm. So this is very good. However, we need to know alpha. We need to know the smoothness of the function. And this is typically not prior knowledge in practice. You're not informed that the function is, let's say, quadratic or whatever. On the other hand, another contribution by Koppe shows that you can obtain square root of t regret by using stochastic gradient, or some people call this the Kiefer and Wolfowitz algorithm. However, the problem is that the function must be sufficiently smooth. In particular, alpha must be greater than 2. So for instance, if the function is not if the function is not is not differentiable at its maximum, then the method fails. It doesn't work. Okay. And finally, a last method that is proposed by Yu and Mano is a stochastic version of the golden section search, or an algorithm due to Kiefer. However, one must know C and alpha as well. So the conclusion is that if C and alpha are known, the problem is pretty much solved. We can get order-optimal regret by any of those methods. However, if the smoothness is unknown, and in practice it is typically unknown, then we pretty much do not know what to do. All right. So what we propose is to expand on the idea of Yu and Mano, which is to use stochastic versions of the golden section search. So let me explain. So what is golden section search? So here, assume that mu of x can be known exactly. That is the noiseless case, classical optimization case. So we evaluate the function at 4 points, x1, x2, x3, x4. So we get the function values at all those points. And what we observe is that mu of x2 is smaller than mu of x3. So what does that mean? So mu of x2 is larger than mu of x3. So this implies that the function cannot reach its maximum between x3 and x4, because otherwise mu of x2 would be smaller than mu of x3. Therefore, we can immediately eliminate the interval that is between x3 and x4, and then we can apply the same procedure to the interval between x1 and x3. And you realize that by doing this many times, we can get arbitrarily close to the maximum of the function. And the reason why it works is simply because the function is unimodal. So now, of course, this leads us to the, let's say, a stochastic extension of this idea, which is to construct a series of nested intervals and making sure that the maximum of the function always belongs to the intersections of those intervals, at least with high probability. It might be that the algorithm fails with a small probability, but if that probability is small enough, that is not going to affect the expected regret. Okay. And in order to construct this sequence of nested intervals, we are going to proceed just as in Kiefer's idea, which is simply evaluate the function at a few points inside the interval, and after we have sampled sufficiently at all those points, eliminate one part of the interval, and then do that again and again and again. And here, one of the pictures that is displayed here is the series of intervals, as well as the amount of time that is spent on each interval. And the thicker the lines, the more time we spend. And that makes sense because the closer we get to the optimal, the thicker the lines become, because we need more and more statistical information to advance when we get close to the optimal. All right. So the first result is a bit surprising. It's a negative result that says that it is actually impossible. It is actually impossible to build a stochastic equivalent to the golden section search. Or in other words, remember that the golden section search samples 2 points inside the interval. If you're given an interval x bar, x lower bar, x upper bar, we sample at the points x lower bar, x2, x3, and x upper bar. So if you only sample at those 2 points, then there exists a unimodal function such that any interval elimination procedure has an error probability of greater than 1/4. And the reason for this, the physical reason for this, is displayed in the picture below. Why is that so? It is because by sampling at only those 4 points, it is impossible to distinguish between the black curve and the red curve. You realize that if I make epsilon arbitrarily small, it's going to be arbitrarily difficult to differentiate between the black and the red curve by sampling only at those 4 points. And this is the reason why there is no stochastic equivalent to the golden section search without some knowledge on the smoothness of the function. Okay, so there is no hope in using this technique. However, it turns out that if you take 3 points inside the interval, there is indeed a technique. So once again, we use the same family of technique, which is, so select 3 points, x1, x2, x3, but all those 3 points, as shown in the picture, are exactly within the interior of the interval. This is the point. If we have only 2 points in the interior of the interval, then we cannot do anything by the previous theorem. Okay, so now how does it work? So we sample sequentially from all those points, x1, x2, x3, and if we can establish that mu of x1 is smaller than mu of x2, then we can eliminate the subinterval on the left, which is x lower bar x1. And on the other hand, if we can establish that mu of x2 is strictly smaller than that mu of x3 is strictly smaller than mu of x2, then we can eliminate the interval on the right, which is x3, x upper bar. Okay, so this is understood. This is always going to work due to the unimodality of the function. The question is, how much should we actually sample? Okay, when should we decide that enough statistical information has been acquired in order to stop sampling and advance? Well, the test we propose is based on the following statistic. So this statistic, we call it the KL star function. So what is the KL star function? K stands for Kullback-Leibler, and KL star of mu1, mu2. So it is equal to 0 if mu1 is greater than mu2, and otherwise it is equal to the Kullback-Leibler divergence for Bernoulli variables between mu1 and mu1 plus mu2 divided by 2, plus the KL divergence between mu2 and mu1 plus mu2 divided by 2. So there is an information theoretic reason why we do this, and it is actually possible to prove that doing this is optimal. This is the optimal stopping criterion if we are trying to minimize the length of the test. So we sample from x1, x2, x3 in a round robin fashion, and whenever t bar of n, which is the number of times we have sampled each of those points, multiplied by the KL star function is large enough, so the KL star evaluated between mu1 and mu2 or mu3 and mu2, then we discard one of the subintervals. So the idea is just to say that when we have sufficient statistical information and one is greater than the other, we stop. And graphically, this is how the function looks like. So on the x-axis you have mu1, on the y-axis you have mu2, and when mu2 is substantially greater than when mu2 is substantially greater than mu1, then the KL star function is substantially greater than 0, and in that case we can accept the test and move on with the procedure. All right. So as I said, there is an information theoretic reason why we choose this test, and this test can be proven to be optimal. This is in the paper if you're interested. So to summarize our results, we proved 2 things. So the first step is to bound the number of samples that is needed in order to eliminate one interval as a function of either mu of x2 minus mu of x1 or mu of x2 minus mu of x3. So remember, we are trying to prove that one is substantially greater than the other. So the length of the test is proportional to 1 over delta squared, delta being the difference between those two values, multiplied by the logarithm of t, and the risk, i.e. the probability that we make an error, is proportional to 1 over t. So this is the reason why, even if the interval procedure fails, it is not going to cause much regret, because it succeeds with a high probability. High probability meaning probability proportional to 1 over t. All right. So the main result is that this procedure that we have proposed, so of course, does not take either alpha or c or any smoothness knowledge about the function, and attains the optimal both regret and optimization error. The optimal regret being square root of t log t, big tau of square root of t log t, and the best optimization error being big tau of logarithm of big tau of square root of logarithm of t divided by t. So it is interesting because it proves that actually optimality can be reached without any knowledge of the function's behavior about its maximum. This is for one thing. And what is even more surprising is that actually it works even when the function is not Lipschitz continuous. You see, all previous work assumed one way or another that the function was Lipschitz continuous, because in optimization, more often than not, this seems like a necessary assumption. If the function changes very quickly, the odds are that you're never going to be able to find its maximum. However, if we assume unimodality, this is not the case anymore, and hence the result. So here are some plots of a run of the algorithm on various functions. So what is interesting is that depending on the shape of the function about its maximum, the amount of time that is spent on each interval drastically changes. When the function is very smooth, then the amount of time spent on the intervals near its maximum become much greater because the function becomes very flat. On the other hand, if the function is very steep about its maximum, then the algorithm does not spend as much time on the smaller intervals near its maximum. So in other words, what I'm trying to say is that this algorithm, without any prior information, adapts automatically to the smoothness of the function. So thank you very much for your attention. And if you are interested in more information, please check out my webpage, which is given here, and I'll be happy to answer questions by emails or whatever communication means that you can think of. Thank you.